Hello, let us see how to apply Fourier transform for the analysis of LTI CT systems. How to obtain the transfer function of LTI CT systems, especially representation of transfer function in frequency domain. So the ratio of Fourier transform of output to that of Fourier transform of an input is called transfer function of LTI CT system in frequency domain. Now you know that the system is represented here, takes an input x of t and produces an output y of t, and the characteristics of the system is defined using impulse response, IMP response, and upon application of CTFT on all those variables, x of t will produce x of j omega, h of t will produce h of j omega, y of t will be equal to y of j omega. So the transfer function in frequency domain will be represented by h of j omega, which will be a ratio of y of j omega by x of j omega. I just want to relate the concept with the convolution concept. We have a system, the system is LTI system, CT system, continuous time system, which accepts an input and produces an output. The input is x of t, output is y of t, where h of t denotes the impulse response. When will you obtain h of t? What is h of t? When x of t is equal to del of t, input is the impulse, then y of t is impulse response. Response for the impulse is called impulse response. So the importance of impulse response is that the response for any input to LTI system will be in future obtained with the help of convolution of any arbitrary input and impulse response. I'll put it in this way. The significance of impulse response is that when a system takes any arbitrary input x of t, if you want to calculate or determine the output y of t can be computed using the convolution of input with impulse response. So impulse response plays a vital role in CT LTI systems, because the convolution formula says integral tau varies from minus infinity plus infinity x of tau into h of t minus tau d tau. Tau is the dummy variable for integration. So I just want to relate the concepts discussed so far. For example, the Fourier transform CTFT of convolution, the result of convolution is equal to, according to the property, it is the product of the x of j omega with h of j omega. Or I'll state like this: continuous Fourier transform of y of t of an CT LTI system is simply obtained by the product of x of j omega with h of j omega. Or in other words, I can say it is y of j omega is equal to x of j omega multiplied with h of j omega. Therefore, h of j omega is the ratio of y of j omega by x of j omega. Transfer function in frequency domain is given by the ratio of Fourier transform of output by input, or you can put it in this way. When x of t upon Fourier transform application, it produces x of j omega, and y of t upon usage of CTFT produces y of j omega. Therefore, h of t, when it is processed using CTFT, should have generated h of j omega. How many different methods through which you can obtain h of j omega? By taking the Fourier transform ratio, or by applying Fourier transform on impulse response, you can generate h of j omega. So transfer function in frequency domain is simply the Fourier transform of the impulse response. So if you use the relationship h of j omega is equal to y of j omega by x of j omega, the response in the frequency domain can be calculated using the product of h of j omega and x of j omega. If y of j omega is a rational function, and if it is expressed as a ratio of factorized polynomial both in numerator as well as in the denominator, there is a possibility to say that j omega plus z1 multiplied by j omega plus z2, etc. In the denominator, in the same factorized polynomial representation, I can say j omega plus p1, j omega plus p2, etc. Right? Using partial fraction, it is possible for you to write a divided by j omega plus p1 plus b divided by j omega plus p2, etc. Where a, b, c are called residues. Now the time domain response y of t can be obtained by just taking inverse Fourier transform from the above expression j omega plus p2. So y of t can be obtained by taking inverse CTFT on y of j omega. And a point to be remembered here is, whenever you have e power minus at u of t, when you apply Fourier transform, it was written as, in the Fourier domain, as j omega plus a. Right? If so, you can simply relate, whenever you get a divided by j omega plus a is simply a into 1 divided by j omega plus a. If you apply inverse Fourier transform, it should be written as a into e power minus at u of t. Got it? So using this, I can simply write the inverse Fourier transform results as a into e power minus p1t u of t plus b into e power minus p2t u of t plus etc. This is how the response of an LTI system can be obtained using Fourier as well as inverse Fourier transform. So you must be given with the transfer function. You must know the Fourier transform of the input. Using these two, it is possible for you to write y of j omega in a factorized manner both in numerator as well as in the denominator. Using partial fraction, you can simply decompose them, and applying inverse Fourier transform on the resultant sequence, you will obtain y of t. So it is possible for you to further proceed inverse Fourier transform of any equation, any transfer function may lead to the output calculation. So transfer function is defined with 0 initial conditions. There is a possibility for you to obtain the response in the time domain, or let me call this response as steady state response. Steady state response. What do you mean by steady state response? It is called the response generated with 0 initial conditions, or it is called in the name of forced response. Only steady state response or forced response can be computed via frequency domain. I'll write the statement here. Only steady state or forced response can be computed using Fourier transform, or let me say continuous for time Fourier transform. So the frequency response of CT LTI system, I'll talk about frequency response of CT LTI system. Yes, how to obtain this? Because you know that y of t is actually obtained, the output of an LTI system is obtained by the convolution of x of t with h of t, or I'll put it in this way: h of t convolved with x of t, and this is according to the convolution formula, integral from minus infinity to plus infinity, h of tau into x of t minus tau into d tau. Assume you have a special input. What is that special input? I'll say x of t is equal to a e power j omega t. Special input. Let me say it is a special input. A is the amplitude, omega is the angular frequency in radians per second. So whenever you are supposed to use it like this, say for example, x of tau, it will be changed as a e power j. So when it is folded, this will become a e power minus j omega tau. You will have this. So I'll represent this as x of minus tau, a e power minus j omega tau. If it is to be delayed further, minus tau plus t shifting. So a e power minus j omega tau plus t, isn't it? Tau plus t. So I can definitely expand this furthermore, like t minus tau will become t minus tau. So this is why do we write like this? Because to compute the output y of t, we require integral from minus infinity to plus infinity h of tau as well as x of t minus tau d tau. Now you will understand the reason for the computation of x of t minus tau, which is equal to a e power j omega into t minus tau. So I can write the final result, applying this into the convolution integral. Y of t is equal to integral from minus infinity to plus infinity h of tau into x of t minus tau. It is a into e power j omega t minus tau d tau. You can decompose the exponential terms so that y of t can be written as y of t is equal to integral from minus infinity to plus infinity h of tau into a e power j omega t separately and e power minus j omega tau separately. Now you can see that the integration is completely over tau. So a e power j omega t is taken outside. The integration is only meant for tau, h of tau, e power minus j omega tau, t tau. Now at last you can find out, surprisingly, this portion is called h of j omega. Agreed? This portion is called h of j omega. Yes. By definition of Fourier transform, y of t, or you can simply take y of t is equal to, most surprisingly, x of t multiplied by h of j omega. So, if a complex sinusoidal signal is given as an input signal to LTI CT system, that is, if x of t is equal to a e power j omega t, if x of t is given as complex exponential sinusoidal signal or complex sinusoidal signal as an input to the LTI system, the output is also a complex sinusoidal signal of the same frequency modified by h of j omega. Output is also complex sinusoidal signal but modified by h of j omega. I'll write the conclusion alone separately. If x of t is equal to a e power j omega t, then y of t is also simply x of t multiplied by, modulated by h of j omega. h of j omega. h of j omega. So, this is how the output is generated. The output is generated. HF. So, h of j omega is called the frequency response of the LTI system. When the input is a complex sinusoidal signal, then the LTI system produces an output. The output is also a complex sinusoidal signal of same frequency but modified only by h of j omega. h of j omega is called a frequency response of the continuous time system. What do you know about h of j omega? What is h of j omega? h of j omega is a complex quantity. It is a complex quantity where it can be expressed as a sum of or product of, for example, h of j omega at an angle of h of j omega, magnitude and phase function. You know that this is magnitude and this is called phase function, right? H of j omega is given by this, whereas h of j omega can also be expressed as a sum of real component and imaginary component. Everybody knows about it. Imaginary component, real component. The magnitude function, for example, h of j omega is equal to square root of h of j omega into h asterisk of j omega. Alright. Whereas h of j omega can be calculated from square root of hr squared plus imaginary component squared is also possible. Magnitude and phase function. The phase function is actually calculated using h of j omega is given by tan inverse of, what is it, real imaginary part to the of real part, hi of j omega by hr of j omega. See, these two are possible only when you know h of j omega as a complex quantity where it consists of real plus imaginary component, or you should take it as if, right, modulus of h of j omega at an angle of h of j omega. So when h of j omega is a complex quantity, it is possible for you to find out the magnitude response as well as the phase response of it. So you know that h of j omega is actually the ratio of, it is called a frequency response, y of j omega by x of j omega, ratio of Fourier transform of output to that of Fourier transform of input. So practical situations, expects you to calculate the output of an LTI system, CT LTI system, with the help of some AFOs and some CROs. In such cases, it is essential to have frequency response analysis. The transfer function of a complicated system is actually determined by using frequency response test only. The design and parameter adjustment of the circuits are all carried out only in the frequency domain, especially by looking at the frequency response characteristics. In frequency domain, the effects of the noise or the effect of impact of parameters, circuit components can easily be visualized, and you can think about going for corrective measures also. So frequency response analysis and designs can be extended to even non-linear systems also, but what we have discussed here is only about linear systems. I'm ready to show you one more example using Fourier transform CTFT. Let me find the impulse response. You know what is meant by impulse response? It is h of t, and frequency response h of j omega of the system described by, say, d squared y of t divided by dt squared plus 4 into dy of t divided by dt plus 3 into y of t is equal to d by dt of x of t plus 2 into x of t. How will you solve this? The first idea is to apply Fourier transform on both the sides, because Fourier transform of d squared by dt squared will become j omega squared into y of j omega plus 4 times of j omega into y of j omega plus 3 times of y of j omega is equal to j omega multiplied by x of j omega plus 2 times of x of j omega. You can just take y of j omega as a common factor from the first equation for the left hand side. So that results in j omega squared plus 4 times of j omega plus 3. Whereas on the left hand side, right hand side, if you take x of j omega as a common factor, you will find out that it is j omega plus 2. Right. So therefore, what you can identify is the ratio of y of j omega by x of j omega. It is j omega plus 2 divided by j omega squared plus 4 times of j omega plus 3, which is given as j omega plus 2 the whole divided by j omega plus 1 into j omega plus 3. Right? This is what is known as h of j omega by definition. So using partial fraction, you can divide this, or you can decompose this into j omega plus 2 divided by j omega plus 1 into j omega plus 3 can be expressed as, say, a divided by j omega plus 1 plus b divided by j omega plus 3. So if you find the constants and their values, they would be of 1 by 2 and 1 by 2. If so, you can simply think about assuming this is equal to 0.5, A is equal to 0.5 and B is equal to 0.5. So you can find out the h of j omega is actually given as 0.5 into 1 divided by j omega plus 1 plus 0.5 into 1 divided by j omega plus 3. This format would be more easy for you to write what is h of t, because h of t is given by CTFT inverse Fourier transform of h of j omega, isn't it? H of j omega, which is equal to CTFT inverse is equal to 0.5 into 1 by j omega plus 1 plus 0.5 into 1 divided by j omega plus 3. So this will be equal to 0.5 into e power minus t u of t plus 0.5 into e power minus 3t u of t is actually the impulse response. This is how the impulse response is calculated, because we know very clearly that Fourier transform of e power minus at u of t is equal to 1 divided by j omega plus a. Using this, you can definitely understand. In some cases, you may be given with x of t. There, the x of j omega is to be substituted. That's all. You can find out. And it is possible for me to determine the frequency response of RL circuit also, which we have seen already, where the excitation source is connected to the center, plus minus the amount of current flowing through is I of t, and the excitation applied is V of t, R is the resistance and L is the inductance. Now you can find out what is the equation, frequency response, as well as determined the frequency response and impulse response of the circuit. Okay, how to do that? Let me start with the solution. As you all know, I of t into R plus L into di of t divided by dt is equal to the excitation. But V of t is considered to be x of t here, and I of t is equal to y of t. So you can definitely write the same as x of t is equal to r into y of t plus L into dy of t divided by dt. So this becomes a differential equation. If you apply Fourier transform, you will identify that this will become x of j omega is equal to r into y of j omega plus L into j omega multiplied by y of j omega. So upon taking y of j omega as a common factor, this will become r plus L into j omega, right? X of j omega is available. So when you take the ratio y of j omega by x of j omega, this becomes simply 1 divided by 1 plus r plus L into j omega. This is actually called as h of j omega. So h of j omega for the circuit is 1 divided by r plus L into j omega, which can be conjugated, or you can take 1 by L as a common factor outside, multiplied by 1 divided by j omega plus r by L. J omega plus A is the general format, isn't it? So when you take inverse Fourier transform of h of j omega gives me 1 by L into e power minus r by L into t u of t. Why? Because Fourier transform of e power minus at u of t is 1 divided by j omega plus a. Simply compare these two and obtain this expression. So inverse Fourier transform will be useful in obtaining the impulse response of any RL circuit also. This is how you need to work on this.